In this video, we're going to take advantage of all our skills with differentiation and use that to find formulas for simple antiderivatives. In earlier videos, we saw that if we started with the function x squared, then antiderivative would be x cubed over 3 plus any constant. And we can check that by differentiating. So everything we put in this right column here, we should be able to get the left-hand element by differentiating. What about other powers of x? So if we have x squared, notice what we got here. We got x cubed over 3 because differentiating x cubed gives us x squared, and we want to cancel the 3 that pops out when we differentiate going back this way. If we generalize that, we would get one higher power here on the right, because when we differentiate, we're going to take one off the power and get back to x to the n. We're also going to, when we differentiate, pop out an n plus 1 that we don't want on this left-hand side. And this leads to a rule that I usually say out loud as add 1 to the power and divide by the new power. That gives us a quick and dirty expression that we can use when we see, say, I want to find an antiderivative of x squared. Oh, it'll be x to the 1 higher power, x cubed, divided by the new power, divided by the 3. We can then combine that with our linearization rules, which says we can break up integrals or antiderivatives if they're added together or subtracted, and we can just evaluate each one separately. If I want to find an antiderivative of x squared, it'll be add 1 to the power, divide by the new power. And then I would add in, well, 3 multipliers, any multiplier constant, we can just keep around, and then find an antiderivative of the x itself. If it's an x already, that's x to the power 1, I would add 1 to the power to get power 2, and divide by the new power. And last but not least, what would I have to differentiate to get negative 2? Well, I'd have to differentiate negative 2x. You can, if you want, call it x to the 0 power. X to the 0 power is 1. If I add 1 to the power, I get x to the 1 over 1. Or you can think of just the derivative rules on their own. Let's just do a quick confirmation. If we differentiate x cubed over 3 and 3x squared over 2 and negative 2x, what do we get? We get 3x squared over 3 plus 3 times 2x over 2 minus 2. The 3's cancel, the 2's cancel, and we get back to x squared plus 3x minus 2. That was the expression we were starting with. So this is an antiderivative of this. Takes a little bit of negotiation, a little bit of practice. Oh, and we also have forgotten one important ingredient. In all of these examples, we could add a plus c without changing the derivative properties. So like this first example, this is our general rule for a power of x, but we'd add a plus c for the antiderivative to cover all the cases, all the possible antiderivative functions. And likewise for this function here, we'd add a plus c. If I put a plus c in here and a differentiate, it doesn't change the answer, so it would be part of the potential antiderivative function as well. That covers our powers of x functions and even polynomials with the use of linear relationships. What about other types of functions? If we have cos of x and we want to find the antiderivative, we should think about what we have to differentiate to get cos of x. A quick check says sine of x is probably a good start. And think back to your rules. The derivative of sine of x is in fact cos of x. No sign, no positive or negative has to be included. So this is perfect with the addition of a plus c. Sine of x, for whatever reason, ends up being a little counterintuitive. It's going to be based on cos of x, but if we think of the derivative of cos, the derivative of cos is minus sine of x. So if we're going to get just sine of x back, we're going to have to add another negative. And this is very similar in feel to the example over here. When we differentiate, we get a multiplier. When we anti-differentiate, we get a divider. If a negative pops out when we differentiate, we're going to need an opposite of that. So we get negative sine of x, which is positive sine of x when we're done. This is what I'm aiming for, so I need to have negative cos of x in my antiderivative. And again, with the addition of the possibility of plus c. We can then combine that with our earlier rules. If we're finding an antiderivative of x, we can add 1 to the power and divide by the new power, but a trig function has a different rule. The antiderivative of sine of x is negative cos of x. And then we can just put one collective plus c at the end. You could put plus c and then another plus c for this, but we could always lump those two constants into one single additional constant at the very end. Clean that up just a hair. There, cos of x. Exploring a bit further afield, what would we have to differentiate to get e to the x? Fortunately, that's the easiest one in the syllabus. E to the x when we differentiate it is e to the x, so e to the x when we anti-differentiate it is also e to the x with a plus c for the antiderivative. 2 to the x is a little more complicated. We just have to remember our earlier rules. The derivative of 2 to the x is 2 to the x again ln of 2, but we're trying to make this match exactly what we had on this side. So what we're going to do is move this over a little bit, give us some room, and we're going to divide that by the thing we don't want. We've got a constant that we don't want, so we can divide through by it. And if we differentiate 2 to the x over ln 2, we'll get 2 to the x divided by ln 2. But the derivative also has this multiplying factor. When we anti-differentiate, we're going to get a dividing factor. So we're going to have 2 to the x over ln of 2 and a plus c. And we can confirm when we differentiate this, we get back to 2 to the x. A little hairier looking here, but actually easier in terms of the formula we end up with. Do we know a function that we can differentiate that gives us 1 over the square root of 1 minus x squared? Absolutely we do. The arcsine of x, when differentiated, gives us this formula. That means when we do the antiderivative, we would say the antiderivative of this is arcsine of x with a potential addition of a plus c. And a similar expression here, arctan of x. And think, what do we differentiate to get 1 over x? We use ln of x. And that gives us the flavor of antiderivatives or antidifferentiation and a toolkit of functions we can use, especially when we think about combining them with summation or constant multipliers. We've covered a lot of territory in the kinds of functions that we can handle now in our antidifferentiation skills. Going back to what this is telling us, because we can find those antiderivatives, the fundamental theorem of calculus is giving us a method to calculate the exact value, the precise answer to an integral, the precise value for an integral. Whereas what we did before with the delta x's or delta t's, the left-hand rule, or even the trapezoidal rule, those all gave us approximations to the exact areas we were interested in. Now we have a way to calculate those areas precisely, exactly, using this antiderivative process. So again, major accomplishment in the sequence of ideas in the course.